So I just got done finishing the simulations page and deploying it. And I had to change some things, but it worked out. And now I think I'm gonna focus on this miners page, see if I can do anything. But I'm not really sure what I'm gonna do because I had an exact idea of what I was gonna do until the simulations page, but now since that is over, I'm not really sure what direction that I'm gonna go. And I ended up creating a new file, not creating a new file, but appending new information to the transactions file, which just so that is faster to load. And yesterday my computer broke when I was trying to, it cut off in the middle of the string when I was trying to open the file and convert to the other format. And I guess it's because the file is too big, so if I'm gonna do anything with that file or if I'm gonna convert it, I probably can't use the computer for a long time until it finishes because it seems like it takes all the processing power of the computer. So I decided to do graphs that are smaller because the other ones were taking a long time to load. And I got down to 900 in some of them, 800 and others 2000 nodes. And I also changed the format a little bit because I thought it would be more interesting to make connections that go from one node to another instead of just analyzing with the way that I was doing before. So maybe I'll study this stuff here now and then try to figure out how to get information for miners. But I don't think I'm gonna be able to. So I think my plan is gonna be to try to develop something by Saturday, but I'm not gonna deploy it. And then I'm gonna have both the version on the local host and in the deployment in case I make progress on this one until then, because I don't want to screw up the deployment just in the day. So yeah. Let me think. So I'm probably not gonna do the backend for the miners part on string. But I guess I can try to search for information about the miners. I know that I have on the database the addresses, so maybe I should start with the addresses and then think about a plan. I'm trying to think about different ways that I can get good questions to get more information. Also, the idea I have in my mind is to do something that displays a graph and then also other information in like a spreadsheet format. But I'm not sure what type of graph I'm gonna do. I don't think it's gonna be with the network X. I'm thinking about doing something with a different format graph, so I'm trying to think about how I can search that. Because the most difficult part about this is thinking about how to connect the backend and the front end when displaying the graph. Because I imagine that the best way to do graphs are probably gonna be in Python. But then if that's the case, I can't really do things the way that I'm doing right now. So I have to figure out a way, unless I can serve the graph through the backend. Let me see something. I think maybe I should start by trying to clarify what are those informations, those columns from the transactions data frame. And then think about the miner stuff as I search for that. Maybe a good question is what kind of information, but yeah, it's probably not good. As miners are intrinsically connected with MEV, which is miner extractable value. So maybe the pending pool. Yeah, I should probably start by the pending pool. So I'm gonna study this stuff here, and then I'm gonna search for the information about the pending pool, which I wrote it down here. Maybe I should do everything on PyCharm before, and then translate. Yeah, I'm probably not gonna do anything on the project itself until I have something figured out here of how to of how what kind of information I want to display, and then think about the graph. Yes, I think it's better to think about the information first, and then I focus on trying to figure out what's the best way to display that. I'm thinking about Stringlit, which is a library from Python that I'm not familiar with, but I've seen stuff about it, and I think it's related to machine learning, that library. But if that's the case, then it's probably going to be hard to connect that with Next.js on the front end. And then the other alternative that I remember looking at was D3, I think, which is a JavaScript library, probably, that allows you to display stuff. But I'm not sure how it works with Next.js. Also remember trying to incorporate Canvas with React.js, and it's really hard because React does things with state, and that's really makes it a lot more difficult if you're gonna have the canvas. There were some options there and some ways to do it, but I remember it was really difficult. A lot more difficult than just doing standard JavaScript. And maybe a last resort case would be to have to do the same way that I did the graphs. I have a static HTML file with some JavaScript, and then I render as a link. That could be an alternative. Maybe I can only get information from the mining from the transaction pool using GIF. Maybe a good question is how can I get the transactions? I think I'm gonna write down some questions just so I'm probably not gonna save this file because I already have too many files, but just for now. I think I remember looking at this, but I couldn't find the information about the methods. Not about the methods, about the information that explains these things here that are received through this method. Oh, here it is, maybe. Another thing I can do is that I still didn't do is work on the search method for the site. But I think that's gonna be very complicated, and there's not a very big payoff, I think. It's probably something that I should delay more. This is very interesting. I also have to look at how to append to the VX formats. How to save a file in VX. Maybe it's probably better to do that for now on. All of these are interesting, to be honest. Maybe I shouldn't put the description. Or I make it like this, probably better. Yeah. Oh, this one is the most interesting. It's all information. I think this kind of answers the question. So I'm gonna paste this first, show see if there's anything more, and then I'll go on to the next ones. I think I already have some minor addresses, so I don't need to search for how to get minor address. I think it just comes with the block information. So now it's more about understanding how to use those addresses in order to get more information about it. Yeah. I'm also particularly interested in understanding if it's possible to uh, attach those addresses to names, just like in Etherscan, because I'm not sure if they did it manually or not. So maybe that's an interesting thing to search for as well. So one approach is to just spend a bunch of time making a list of all the addresses, and then you just filter or you create a dictionary, something like that. But that way is obviously not that good because then you have to manually update and yeah. Oh, the other thing I was thinking about was Polygon. Now I remember. So I should probably search for that as well. I'm not even sure if it's possible to get information from Polygon because I think it's private. Might be wrong about that, but I remember seeing that you can get information through Google BigQuery, but ideally I want a method that doesn't involve anything, doesn't involve Google or a big company. And the biggest problem is that I can't use all the information that I have. That's the thing. Because of the data frames. So I have to think about a smarter way to do things. I think I'm gonna erase this one because I already solved. Yeah, this one is probably the best. Transactions, and then I'll go one by one. I really like the documentation on Ethereum. I think it's really good. Why is everything Russian? Is this Russian? I think. Not really sure what language. Maybe it's Indian. I don't know. The fuck is going on? No, Azerbaijan. Yeah, so I think I got it. There we go. I'm gonna start by this one. If you think about it, the blockchain is kind of like a linked list. Works pretty much in a similar way, I think. And it uses the try structure. I think when I go back to studying lit codes, which I think I'm gonna do after the demo day, I'm probably gonna do tree graphs and then Merkle tree, not Merkle tree, but try, whatever it's called, and linked lists because it's probably more related to the blockchain. It's probably gonna help me search data and do things on the blockchain. I think I'm gonna watch this video. Let me see first. I'm gonna watch this one. I'm gonna watch it really fast. And then move on to the next topics.
Get very easy to understand by stepping through the key pieces of what a blockchain is in a visual way. But before we get started, we need to take a look at this thing that we call the SHA-256 hash. Okay, and a hash, this is one of them right here. A hash looks like a bunch of random numbers. And essentially what it is, it's a fingerprint of some digital data. And it just so happens it's a fingerprint of whatever I type in this box. So if I type my name, Anders, into this box, you see that the hash has changed. Matter of fact, it changed every time I type a letter, right? So I'm gonna go back to this. So it says Anders. Okay, so this is the hash of the name Anders, all lowercase. It starts with 190A, right? Okay, so if I delete that and I go again and type Anders again, you can see it starts with 190A, the same exact hash. In essence, it's a digital fingerprint of this data. Whatever data is here, every time you type exactly the same data, you get exactly the same hash. And I can type anything I want. So I could even have nothing, like just, E3D0, that's the hash of nothing. Or you could type tons and tons of stuff. As a matter of fact, you could put like a Library of Congress in here and you would get a hash. And the interesting thing about it is, regardless of if there's a tiny amount of information, no information, or the entire Library of Congress, you're always going to get a hash that is this long, this many characters. So you're not going to be able to pre-guess what this is. You're going to have to put the Library of Congress in here to figure out what the hash is, but you'll always get exactly the same hash regardless of how many times you put exactly the same information in. So what I'm going to do is extend this idea of a hash into something that we're going to call a block. All right, so let's take a look at a block. So this is a block, and it's exactly like the hash. It's just that data section I've broken out now into three sections. One called block is just some kind of a number. This is block number one. A nonce, which is just another number. We'll go into what that is in a second. And then there's some more data, just very similarly to the way we had it before. However, the hash of this, which includes all of this information up here, is down here, and it begins with 4 zeros. You see that? It's a relatively unusual hash. Most of them are not really going to start with 4 zeros like that, but this one happens to. And because it does, totally arbitrarily, I'm going to say that this block is signed. Okay. So what would happen if I were to change any one piece of this information? Let's say if I were to type something here, right? The hash is going to change. And what's the chance of that if I type letters, this hash is going to start with 4 zeros? Pretty low. It's probably not, right? So let's see what happens when I do that. I'm just going to say hi. Oh, look at that. Right? This hash does not start with 4 zeros, and so the big background here is turned red. So now you know that this block with this information in it is not a valid or a signed block. Okay, and that's where this nonce comes in. This nonce is just a number that you can set to try to find a number that fits so that this hash starts with 4 zeros again. Right, so how do we do that? Well, let's start with 1. Does that start with now? It's 3, 2, now. Let's try 2, FF now, 3, 4, 5, 6. You get the idea. Like I could sit here, there's one that starts with 0. I could sit here all day typing these numbers and trying to figure out one that actually is going to hash out to something that starts with 4 zeros. It's going to take a long time. So here I have my little mind button. I'm sure you've been wondering what happens if I press that. So what's going to happen when I press this mind button is it's going to run through all the numbers from 1 all the way up to try to find one where the hash starts with 4 zeros. And this process is called mining. Let's do it right now. So now it's checking all of the numbers from 1 all the way up there. Now it stopped at 59,396, and that one just happens to hash out to something that starts with 4 zeros, and it satisfies my little definition of what a signed block is. Okay, so that's a block. Now can you tell me what a blockchain is? It's probably just a chain of these blocks. So how do you put them together? Let's do that. All right, so here's my blockchain. I have block number 1. It has some kind of amounts just like before. There's some data area 2. But then it has this previous. Here's a bunch of zeros. Let's roll forwards. This is block 2 and block 3 and 4. This blockchain has 5 blocks on it, right? The previous here starts with 00 AE8, right? Is this number AE8? And then this previous, B90 is this one over here, B90. So you can see that each block points backwards to the one before it. You remember that the first block over here there actually is no previous. It's just a bunch of zeros. It's actually just a fake number. Okay, so just like we did before, what happens if I change?
It's exactly the same as the linked list. At least when it comes to this stuff, where each one has a pointer to the next.
Some information here, right? It's going to change the hash of this block and it's going to invalidate, right? Well, let's try that. So I'm going to type hi again. Sure enough, that block is invalid, all right? Just as we assumed. But what would happen? I'm going to fix that now. Go back to something that worked. What would happen if I change something in this block? Right? It's going to change this hash, but this hash gets copied up to this previous. So it's going to change this one too, right? So it should break both blocks. So let me try typing hi in there. Sure enough, right? So we can go back as far as we want, to some point in the past and break that block, and it'll break all the blocks since then. Everything before is still green, but this one is red. So if I wanted to, change something in this blockchain, I could just go over to block number 5 right here. We could change it. I'll put hi, and then we could remine it. Pick a different nonce. We'll do that right now, and we could essentially alter the chain. So we've done it. So that we should be good now, right? All right. Well, what happens if I go back in time to here and I break it here? Now I have to mine this block, which will pick a nonce that makes this block hash out to 4 zeros. If we can find one, sometimes it takes a while because it's got to run through a lot of narratives. I found one at 138,000. All right, but this one is still broken because although this one starts with 4 zeros, adding the 4 zeros with different stuff up here still makes this block hash out. So I also have to mine this block. All right, and that takes some amount of time. That one's a little bit quicker, and then I have to mine this block to fix it. All right, so what we're showing here is that if I go and change this last block, all I have to do is remine this block. If I go way back in time to back here and I make a change like that, I'm going to have to mine this one, this one, this one, and this one. So the more blocks that go by, more blocks in the past that we are, the harder and harder and harder it is to make a change. And so that's how a blockchain is going to resist mutation, resist change. Okay, so now, I did if I do this in this block here, you can see that I've changed it to hi and remined it, blah, blah, blah. How would I know that my blockchain has been remined? All right, let's take a look at that. I'm going to hit this little distributed thing. So now we have a distributed blockchain. It looks exactly like the last blockchain, okay, up to 5. But this is tier A, the first tier. If we go down here, you can see here's tier B, and it happens to have an exact copy of the blockchain. There's actually also tier C down here. And this can go on forever. There's many, many tiers out on the internet, and they all have a complete copy of the blockchain. So in this case, if I look at this hash, it's 00E4B, right? If I go down to this one, I notice it also has E4B. If I go down to this last one, it has E4B, so they must be identical. And I'm going to demonstrate that by going here and typing something. I'll type hi again, and then I will remine this block. I've got some other number, and I'll put some other number up here. So I should be able to mine this block. Okay, now all the chains are green, right? They're all green. However, this chain says the last hash is E4B. The bottom one says that 2E4B, and this middle one here says 4CAE. So I know just by glancing at this one little hash that something is wrong in this blockchain, even though all of the hashes start with 4 zeros. I know that this one is different, and it's different because I have two. It's essentially 2 against 1. We're a little democracy here, right? This guy argues that it's E4B. This guy argues that it's 4CA, and this one is E4B. So E4B wins. So that's how a completely distributed copy, having a copy on many different computers, they can all very quickly see if all of the blocks are identical. Remember, blockchains can have 400,000 or 500,000 blocks very easily. So rather than checking through all of them, all you really have to do is look at the hash of the most recent one, and you can see that if anything in the past, anything way back here was altered, you can tell by looking at this at the last block in this in the chain. It's going to hash out something that doesn't start with 4 zeros, and it looks very different from what the hashes on the good chains are. Okay, so that's a blockchain. That's the entire thing. There is no more to it than that. But it's kind of not really useful because we don't have something in this data area that means anything. I keep typing my name or hi, and it's kind of sort of irrelevant information. So what we really want is a token. So let's do a token on our blockchain. All right, now look at this. So I have this token just totally arbitrarily. I'm calling these guys dollars, right? So we have $25 from Darcy to Bingley, $4.27 goes from Elizabeth to Jane. You get the idea. It's basically there's all these transactions that are happening, and I just replaced the data with these transactions. And just like we saw before, so there's multiple blocks here. This one has more transactions. It doesn't matter how many transactions there are. There can be many, there can be few or none. If we keep going forward here, just like we saw before, if we go down, we notice we have all these other copies of the same blockchain, right? So now here's where the immutability is important. If I change something back here, you'll notice that this is A7FC, blah blah blah. It's something else. So it's something different than what's down here. So in this way, I mean, it's very important that if I were to go back in time and change some value, that we would notice. It's very important with money that you don't lose track, and that's the whole point of using a blockchain here. It's the whole point of resisting any kind of modifications, of things that have happened in the past. So that's the reasoning behind using a blockchain to remember tokens. Now, one thing I would mention here is that we're not listening. Darcy has $100 and he's giving 25 to Bingley. The only thing we're saying is Darcy gives 25 to Bingley. We're not remembering a bank account balance. We're only remembering money movements. So this begs the question: does Darcy have $25? Well, we have a problem here in this version of the blockchain. We don't actually know if Darcy has $25. So let's look at a Coinbase transaction. So if we look back here at Coinbase, we're going to add a Coinbase transaction to our blocks, and this is very similar to what we've seen before. But we're just adding Coinbase at the top. What that's saying is we're going to invent $100 out of thin air and give it to hundreds. And there's no transactions in this block because nobody had any money previous to this. In the next block, another $100 comes out of nowhere and goes to hundreds. I'm a fan. I love it. Right? We'll take $100. Now we have some transactions. You can see that they're all from hundreds, all from me because I'm the only one who has any money at this point. So I'm sending 10 of my dollars to Sophie. Do I have $10? Yeah, I do. I look back and I see that this Coinbase transaction has given me 100, so I have these 10 and I can send it on. And you add all these up and you don't go over 100, and it follows sort of the basic rule of a currency. Like you can't invent it out of thin air. You can't create money out of thin air. It's dispersion is controlled. So now if we look at this blockchain that we've created and we zip forward in time and we notice that we see that Jackson is giving Alexa $2. And so does Jackson actually have $2 to give Alexa? We go back to the block before and we see that Emily, who had gotten $10 from others, gave 10 to Jackson. And so Jackson does have money. So we can just go backwards and find that out. And that's actually one of the benefits of having a previous here. It's easy to go backwards. We just look for the block that looks like that has that hash, and here it is right here. Right, so it points the blocks back in time and allows us to trace the provenance of any coin that we want. So that's a basic blockchain, and we're running a currency on top of it. And as you know, blockchains are there many copies. Everybody has a copy of it. So if we mutate, this and make it $6, these go invalid. It does not agree with these blockchains down here. These copies of the same blockchain down here. So this resist tampering, which is what you want for a currency. It works very well for things that are small and transactional, like this. I'll go ahead and fix that. And they're just a very efficient way to handle agreement on what has happened in the past. It's kind of this immutable history that goes down with time. So that's a basic blockchain and a token on it. We're glossing over some main points, but if you dig into the demo and click through these things and play around with it, you get a better and better idea of how this works. There will be a part 2 where we go into a little bit more detail about how the transactions are created. Till then.
Yeah, this is really good. Mostly a review, I think, for me. So let me keep reading this stuff. I think I can watch videos on this. I'm not gonna. Not gonna read this. This looks really interesting. I think I'm gonna watch this. No, I'm gonna watch it later, probably. I think there's two things that I need to know more. One is how the addresses are interacting in the chain, because I understand the stuff there that I just read about the blockchains and the transactions and each block linking to the next one, but it's not really clear to me yet in my mind how they interact. Like, what's the difference between the miner address and normal addresses and smart contract addresses when they are making these transactions? And what's the link between that and the VM? I think that's the main point that I have to clarify. And I think the difference, they're all transactions basically, but the difference between smart contracts, like the article is saying, is that the smart contracts, they activate parts of the VM, the stack machine, and the normal addresses don't. But then I'm not sure how the normal addresses, like what happens when you send a transaction with MetaMask, for example. I think I need to clarify that. Maybe you should search for that. How personal wallets work under the hood. I think the smart contract programmer, or something like that, he has a video on that. I think I'm gonna watch his video, search for his video. The problem with watching these videos is that most of them talk about stuff that I already know, and they're the more basic stuff. It's kind of hard to find the videos that I'm more interested in right now. And maybe this one is a good one. I think this one also. This guy here. I think I'm gonna watch these videos. I remember reading this as well a couple of times. And I think I get it, but it's good to read for a spaced repetition. And I'm still not sure if I completely understand exactly how it works. I guess I understand the pieces, but it's hard for me to connect everything. I think I watched the course on ZTM about Go. Maybe I should watch that again. I could have it save it here. Saved. Oh, I think I watched, but it didn't save. And whatever, I can just look on YouTube anyway. And if I remember correctly, it's pretty similar to Rust. Different, but similar in some ways. Oh, these videos. I forgot about these videos from Austin. Maybe I should watch these ones after I watch the smart contract programmer stuff. I'm gonna finish reading. I'm gonna finish reading the other article and then I'm gonna watch the videos. And then I'm gonna continue to search for the questions here, I think. If I remember, I saved a video on the watch later about this. That's probably gonna help. Yeah, probably as I go through this, I'm just trying to clarify things more. And it's gonna take me some time, I think. Even after demo day, I'm planning on after demo day to study, to do 1 or 2 hours of lead code on graphs and trees first. And then after that, spend a lot of time trying to study and clarify my mind on everything related to the blockchain and how it works, how everything works, because I think that's gonna help me a lot. It's pretty much everything that I'm doing anyway, which is analyze the data. So I need to know exactly how everything interacts with everything else. So as I'm building stuff, I know what I can and can't do. And then I think only after that I can start thinking about how I can use this data to make different conclusions. about what's happening in the blockchain. And I think I remember now that one of the main things I wanted to do essentially in the beginning, even before Nights and Weekends, was related to Polygon, because Polygon is obviously a lot cheaper to deploy contracts and to send transactions. So hopefully there's a way to get information on Polygon, because then I can build a lot of things that are connected with the stuff that I already built with Polygon and use the data to automatically, maybe I can code some smart contracts and then connect those smart contracts with logic from the data analysis and then create bots, things like that. I think that would be very interesting. And that's kind of what I want to do. But first, I think it's more important to gain more clarity over how everything works and what exactly I can and can't do. Because in my mind, it's usually very different than as you study, you gain more clarity over what's actually possible and how hard it is. Same thing that happened with the data frame, where I just realized now that is very slow. So because I have this vision and it's probably very incorrect based on what is actually possible. So the only way to realign and gain more accuracy over what's actually possible, I think, is just studying all this stuff first. But it's kind of difficult to know what direction I want to go. Because up until now I had it very clear until demo day, because I knew what I wanted to do until demo day. But now that I have finished all the other stuff, it's kind of hard to pick which direction to go with and what exactly, because I have so many ideas and there's so much stuff that I have to study as well. And in order to make it happen, to make it work with machine learning and more advanced analysis, I don't think I can do it now because it's going to require more storage and it's also a lot more complicated because of things like day speed. So I probably need GPUs and stuff like that, and I don't have the money right now to buy it. So I think that's why I'm struggling to think about which way to go with and what exactly to study. Because I have to find something that I can do that it doesn't require having a bunch of data, or that I can do automatically on the fly. So one thing that I was thinking about with the graphs is, instead of having a bunch of graphs, I can just do on the page that the person selects a time frame, and then I put the limit for 2000 nodes so that the graph is not slow. And then I create the graph on as the input, after the input. So that's so in this case you wouldn't need the whole information of the blockchain, and you can do a bunch of them sequentially, kind of like batch. But then it's obviously a lot more complicated. So I was thinking about doing kind of the same thing, but in a different way for the analysis of other stuff. Because I don't have the, if I build these large data frames, then it's gonna be too slow. And also I don't have the computation. Also wonder how faster it would be if I coded this on C++. But I think it's probably deviating too much from what I'm doing, and that's the problem. I guess that's the thing that I'm struggling with, because I have the vision, the overall vision of what I want to do, but it's really hard to come up with the details because there's so many concepts related to each other, and I need to know the mathematical equations, I think, for each one of those things, and then translate those mathematical equations into computation. When I think in my mind, I'm thinking about the graphs and how those concepts interact with each other in the abstract form, but to be able to put actually write down the physics of it and how each thing connects is really hard. Especially just looking at the numbers in the data frames. Like how I'm gonna go from those numbers from the vision I have. What kind of stuff is missing that I can do incrementally, and it's not gonna be extremely hard to do. Yeah, I guess the main thing that I want to do is relate. That's the thing. I want to relate the economical transactions with the data flow of information in social structures, and associate that with the relationship between the limbic system and the prefrontal cortex. So kind of use the blockchain as a way to simulate the dynamic from the limbic system to the prefrontal cortex, and try to calculate the frequency that of adjustment and the moment of inertia from the limbic system to, and how the prefrontal cortex regulates the moment of the inertia from the limbic system. That I think it works like a pendulum depending on mass. But that's easy to say, and it's really hard to think about how I'm gonna do that, because then it involves get information and data about the limbic system and the prefrontal cortex. But maybe not, actually. I think the problem is how I'm gonna categorize these things. That's the challenge, I think. Because in my mind it makes sense when you talk about these things, but then how do you put that into the information? Yeah, that's the problem, I think. How do you categorize what's limbic system? Is obviously a gradient, it's not polarity. But how do you see I guess I can do simulations, and then from those simulations I can estimate, because it's gonna be a gradient, it's gonna be exponential, I think. Yeah, it's probably, yeah, I think that's probably the way to go, actually. There's probably gonna be a fractal pattern, and it's gonna be a change in normal probabilistic distributions into exponential distributions. So maybe I can use the transactions to gain. Yeah, but then the question is how. That's the challenge, because how are we gonna abstract the fractal pattern from all the transactions, because there's always volatility and it's hard to, you need massive amounts of data, I think. Because otherwise, how are we going to differentiate what's part of the fractal pattern and what's just a noise? I think this is what I need to sit down. First, I need to clarify all this stuff that I can get from the blockchain. Then once I have that really clear and I understand how everything, all the pieces go together, maybe I should draw this stuff. And yeah, that might be a good idea actually. Because then I'm gonna have a clear vision of how everything connects with everything else. And then once I have that part, then I can start thinking about how I can associate that with mathematical equations that are gonna relate the dynamic, the flow of the money. So the patterns of transactions and the value with mass and with mass and moment of inertia and gravity. Yeah. And then training machine learning models on that. Yeah, but then the question would be how I'm gonna get how I'm gonna associate that with the distribution of the limbic system to the prefrontal cortex. Because the way I envision, the way I imagine is it starts at the root here, at the neck, which is instincts, and then it goes all the way for the forehead, which is the imagination, and it's kind of like a tunnel, which is more of a feedback loop system, because everything in reality is a feedback loop system that is interconnected with all the other feedback loop systems, like a multifractal structure. And so there is this distribution of, and because of power and the mass that it has, it dictates how the structure changes over time. So it probably follows a 20 Pareto distribution rule, just 20% for the prefrontal cortex and 80% for the limbic system. And because the limbic system has the mass, it's like it works like a pendulum, or more like a harmonic pattern, like a sine or cosine wave, where the mass of the limbic system is balanced by the prefrontal cortex, and then that generates power over time, and the power when filtered through the lens of the market economy, which is the relationship between the limbic system and prefrontal cortex, makes the cycle self-destruct because it polarizes the structure. Over time, because the abstraction evolves faster than the intuition and then creates more power, and then the power raises the tension because it's being filtered through the lens of the market economy, which is the balance. Yeah, I think the market economy is this balancing act between limbic system and prefrontal cortex. So I think that's what I have to figure out as what's the frequency of change. But then that's the problem, because how do you categorize limbic system and prefrontal cortex? How do you see the distribution in the patterns of transactions? And I think it has to be multifractal or fractal in the essence. So there's going to be a fractal pattern in the transactions. So I think I need to capture that fractal pattern. And maybe run simulations with time to see. But then is the balancing act between overfitting and underfitting. Because obviously this fractal is going to be connected with all the other fractals which has infinite complexity, because that's the nature of, probably the nature of the universe. So there's always going to be lack of accuracy, even if I find a multifractal pattern that closely approximates the relationship between limbic system and prefrontal cortex, that makes the feedback loop system of the market economy of impulses becoming innovation through the lens of market economy, which eventually polarizes the structure, because it's kind of like a battery. It adds power over time through technology, and that technology makes the cycle lack harmony. Yeah, and then after that, so that's the main thing that I have to think about. Is how to closely how to create a system that closely approximates the tendency of the exponential distribution of markets, because the regulation forces are not strong enough to recalibrate the structure, so everything eventually becomes the winner takes all dynamic from competition. And so the challenge is how to calculate the frequency there. I should put that in a mathematical framework, I think. Like a Watt's time frame, and exactly what is the magnitude of the regulation forces and the expansion forces, and at what time frame the system starts deviating towards the exponential distribution. And then after that, figuring out a way to create systems that are capable of regulating or balancing in a way that exponential attack and the exponential power doesn't corrupt the structure. And obviously, it's easy to say these things, but it's really hard to do. And to think about the details and what's the next step that I have to take. That's why it's kind of difficult to think about all of these questions and which one makes more sense to what I'm trying to do right now. Like, what's the next step? Especially if I can't do all the computation, which obviously companies like Google and Amazon and Meta are probably doing. So this is one thing that worries me about this trying to do this, is because if they have they probably thought about these things. So if they have all the computational power, why they're not doing this stuff? So and I imagine the reason why is probably because there are roadblocks in the way that I'm not seeing right now. But guys, I'm just gonna learn it as I go, because that's the only thing I can do. So yeah, I guess that's my concern, that I'm assuming some things are true because of the vision that I have and all these principles, but I'm missing some details that make it extremely hard to figure out something like the nature of the universe being computationally reducible, and maybe you can't train machine learning to approximate the fractals because of the calculation of what amount of computation would be necessary. That might be the case. Or maybe they didn't think about it, but I find it hard to believe. Oh, there we go. But I don't think they're gonna talk about it. I wanna know what these things are here. Oh, there's also this stuff that is different, which is the smart contracts. Hmm. I guess it can be viewed in the same way. It's pretty much the same thing, I think. But in companies, it would be technology instead of smart contracts. But it's pretty much the same dynamic. So maybe there's also a correlation between, yeah, it closes the feedback loop system with smart contracts. So you have supply and demand, and then technology in the middle, or something like that. And the technology is the thing that makes the cycle out of sync. Maybe not. Maybe it's just actually human dynamics, probably. But as a byproduct of that, you have technology, because that's the natural equilibrium of uh, the market economy in relationship to social structures. I guess that's the thing. You can't really classify technology, so it would be impossible to predict which innovation is gonna happen. So I think that's useless to think about. But it might be possible. I think the best direction to go is try to understand how, but that's the challenge, because you're never gonna know how much the tech is gonna impact the overall cycle, because it's how can I say, you can have black swans or unlikely events that change everything, like the internet, or but usually, because that's the thing, usually it's gonna follow multifractal pattern, because everything in the universe is a multifractal pattern. So to some degree, it has to be predictable. Otherwise, gravity wouldn't exist and time wouldn't exist as well. There needs to be some degree of predictability, and I think that's gonna be a multifractal pattern. So even though definitely won't be able to predict what technology will happen. I think it's possible to create a system that is better at adjusting the innovation in relationship to the current state of the system. So it has a faster response, let's say, and more efficient regulation. A blockchain, if you think about it, is pretty much the representation of a market economy. I think it's exactly the same thing. Because everything is a transaction between people. And then you have technology, which is the smart contracts, and in normal money is the business, the computers, stuff like that. Yeah, maybe it's different, but I think it's similar enough. And that's the difference. So maybe you can see if it is a smart contract or not by seeing if it has code hash. So maybe this is a good one to write here. But maybe not. Oh, actually, yes, because the balance is here. I was gonna say maybe this is not a private account because it doesn't have storage hash, but it has the balance. Storage hash, I think, is when you make a smart contract and you can receive money, so it's gonna store a bunch of money from a bunch of different other addresses. So I think that's the difference. And this is really good, but I think I'm gonna save this for later. What is this? Oh, 0 with contract creation. Interesting. So I can just filter based on this, and I can see, oh, maybe that's an interesting way to get the names. But I still would need to search manually anyway for the addresses of business in order to connect that address with a real name. But I could make a list of all the contract creations. I think that would be interesting. Because I think, yeah, if I do that, then that will allow me to filter all the data and see based on those. Yeah, maybe that's a way. That's a way I can do to differentiate account addresses from smart contracts. I just filter everything based on. I just get a data frame that has all the contract creations, and then through that I get the addresses, and then I filter the other ones. Yeah, but then it would be very inefficient because I would have to compare each new address with all the other addresses of the contract creations to see if they are included in the data frame or not. So probably there is a better way. I hope they talk about these things here. Should have no idea what it is. I guess Web3 is not owned by anyone, I think. Or maybe it is. But I guess it's the same people probably that created Ethereum. I'm not really sure. Yeah, but then the provider is a different company, so. And I think you have to use the RPC. Or maybe not, actually. Maybe the Web3 is directly from Ethereum, and then you can, if you have your own node, you can use the Web3 library to communicate with your own node, like I was reading in the other articles. So the RPCs just facilitate the process, but they are not necessary, I think. This is really good actually. I'm gonna save it in case I wanna look at it later. So far, I think it's the best, most simple explanation of the EVM I found, of how it works. Obviously, the yellow paper is probably more detailed, but this is really easy to understand. I'm gonna finish reading this, then I'll go back to the other one. I forgot to pass these ones there. I think it's the same video. Yeah. I don't like how they explain the more intuitive ones and they don't talk about these ones. Which there's no clue what this might be. Yeah, they don't talk about what those things are. It probably doesn't matter that much anyways. This makes me think about how each transaction generates the OP codes through the AVM. It's probably based on the rules of the AVM. I'm not sure if that's that is important for what I'm trying to do. It doesn't seem to be, but maybe it is if I want more accuracy. Probably. Yes, probably is actually, now that I think about it. Because understanding the transactions and how to translate that into OP codes allows more accuracy in the analysis of the data. Because you can classify more what each transaction was for. Yeah, but I think this is probably something that I'm gonna see later. After if I deal with the miner stuff and separating transactions, separating accounts from smart contracts, and gain more clarity. Oh, these are signature values. I'm not exactly sure how it works, but signature value. At least it's something better than nothing. Maybe I should put them together. I saw this, but they didn't talk about what each type of transaction means, what it means for transactions to have different types. Or maybe I should go back there. I think it closed already, so never mind. I also remembered also have to read this stuff here about the attacks. I'm probably gonna read this after demo day. And this is related to the other stuff, to the stuff that I'm doing now. So that I remember that I left open because I wanted to see. Yeah, I guess the biggest thing that I have to do, maybe I will start with uh, adding the data to the VAX file format, because that's the essential thing that I need if I want to be able to analyze large amounts of data. Otherwise, it gets too complicated, I think. I think it's still possible, but I'm gonna have to do a lot more code, because then I'm gonna have to separate each file, and then I'm gonna have a bunch of files in a directory, which is also possible, but I guess that's something I could do. I have one file for blocks, one folder for blocks, one folder for transactions, and then I limit the size in the code as I get the data for the data frame, and then it just keeps increasing by some arbitrary number, or then I change the name of the file that is going to be saved, and then I just create a bunch of different files until I have the 16 million blocks separated by a bunch of different files. But it doesn't seem like it's a good approach. It would be much better if I could figure out how to... I still think I'm gonna have to split the files anyway, because it's too big, but at least I'm gonna have less files if I do it with the VX library. So I need to figure out how to get from the Web3.js into a VAX format file, HTF5, I think. VAX. It was written in Go, this probably. Yeah, it's probably Go, actually. Instructions.go. So the EVM is written in Go, I think. Yeah, this is probably the source code. Interesting. Yeah, source coding diff. I don't think Go is that hard. I remember a little bit, but not. Maybe I'll watch a video or two about Go. just so I have an idea. I remember when the first time that I did the node, I did it on the terminal, so I think it's probably possible to do it with a normal file, which is gonna be way better than using the terminal. And then I can write everything in Go when it gets time for me to build my own node. Yeah, I guess that's probably the best way. To run my own node and then use Go to interact with the node. Or maybe hash should be on the console. Which is kind of bad. Cool. Probably gonna look at that in the future. I'm gonna watch these videos now.
Ether, and we also know how to send Ether out from contract. So today let's build a simple contract that can receive Ether and send Ether out of the contract. The name of this contract will be called Ether wallet. Anyone will be able to send Ether into this contract, but only the owner will be able to send Ether out of this contract. So we first declare a variable that stores the owner of this contract. So I'll type address, public, and then declare it as owner. Next, we'll initialize the state variable owner inside the constructor. So I'll type constructor, and then say owner is equal to message.sender. We want to enable this contract to be able to receive Ether, so I'll declare the function receive external payable. Now this receive can be replaced with the fallback, and it's going to accomplish the same thing. However, here we want to make our intentions clear that we only want this contract to be able to receive Ether. And if someone calls a function that does not exist inside this contract, then we want that transaction to fail. So instead of fallback, here we'll use receive. And the last function that we're going to need is a function that can send Ether out of this contract. I'll name this function withdraw. And the owner will be able to specify the amount of Ether to withdraw from this contract. So the uint amount, this function will be external. And we don't want anyone to be able to call this function. We only want the owner to be able to call this function. So I'll say require message.sender is equal to the owner state variable. And if it is not, we'll say caller is not owner. Once we know that message.sender is the owner of this contract, we'll transfer the Ether from this contract to the owner by typing owner.transfer and then passing the amount that we're going to withdraw from this contract. Now, if I try to compile this contract right now, we'll get an error saying that transfer is not available for the address owner. So what we have to do over here is to declare the owner as payable. So here I'll type payable, and then I'll cast message.sender as payable, compile the contract, and the contract compiles successfully. Now, basically, we're done with the withdraw function, but now I want to optimize for gas. One of the things that you can do to save gas is to replace state variables with variables inside memory. So here, owner is a state variable, and we know that message.sender is the owner, so we'll replace this with message.sender. Since message.sender is not a payable address, we also need to cast this as payable. Replacing owner state variable with message.sender, this should save a little bit of gas. Now, instead of using transfer to send Ether out of this contract, we could have used call to also accomplish the same thing. So these two code transfer, and this two lines of code accomplish the same thing. For today, we'll use transfer. Before I deploy this contract and show you a demo, I created a function get balance, and this will return the amount of Ether stored in this contract. So let's now compile the contract, and then deploy it, and we'll send some Ether and then withdraw it. So we'll send 1 Ether, open the contract, and then call transact. Next, we'll call get balance, and we can see here that there's 1 Ether stored in this contract. And lastly, we'll withdraw all of the Ether. So I'll call withdraw. Actually, to show you that only the owner can call withdraw, I'm gonna scroll up, switch accounts, and then try to withdraw someone now. Call withdraw, and you can see here that the transaction failed because the caller is not the owner. So I'll switch back to the owner, and we'll withdraw all of the Ether stored in the contract. Call withdraw, and the transaction is successful. Check the balance, and the balance is now 0.
I guess the wallet is just a smart contract. It keeps track of the balances of different addresses that's signing into the contract with a private key. It's kind of not that hard, actually. Maybe I'm overcomplicating in my mind. But for some reason, it's really hard to visualize how it works. How MetaMask works, for example.
Well, let's check it out. So it's kind of like a fingerprint. You have input, and it can be anything. For now, we'll just go with the text "Hello World," and on the other side, you're gonna have an output. And that output is a 64 character. Yeah, it says 66, but that's because it's 0. It's a 64 character hexadecimal string. And if you look at hex, it kind of looks like a color, and it might even be easier to kind of describe what we're seeing here if we just make it a color. So let me throw together just a color depiction of what this is to help illustrate what the heck is going on. So what we're gonna do is just grab these first 6 characters of whatever the string is and display it as a color. And if we look at that, we'll see that it's that 47, just like we wanted. And there we go. It's like nice purple color. So let's see what color my name is. There we go. Nice forest green. Cool. So now let's go back to Hello World. It's that purple again. Okay, so what we just discovered here is it's deterministic. Basically, whatever we put in as our input, we're always going to get the same thing out on the other side. Okay. The second property here is you can put in anything of any arbitrary size. So I can just match on the keyboard. We can see the color changes, but that string stays at that 66 length, right? So no matter what you put in here, even a file, right? I can drop in this file of Leo, my boy, and I can put that in as a hash, and I'm going to get that's slow. This nice orange color, right? And then I can drop in something else that I have a BIP word list text doc laying on my There we go, and it's this nice light blue. So if I bring Leo back and I drop him in, guess what color it's going to be? We know what color it's going to be. It's going to be that orange, right? So you get this deterministic fingerprint of the thing that you put in, and the next most important property is it's one directional. So what I mean by that is, let's get this file out of here. If I put in hello world again, we're going to get this 4717. If we take that 4717 and we send it to someone, and we say, okay, here you go. Here's the hash of my secret. If you can guess my secret, I'll give you $100. They're not going to be able to like get close, right? So let's say it's 4717 and they start like poking around waiting to see if they can find a 4. They found a 4 by typing in hello, right? You can't just like change little characters and get close. You either get it or you don't, and you have to basically brute force guess it. So if they happen to guess hello world, they're going to get the answer, but if they don't guess it, they're never going to get it. There's no way to get closer to figure out if you're getting it. And that's, you'll find out a lot with cryptography is it's sometimes frustrating as a developer because it either works or it doesn't, and you don't get any hints about if you're getting close. But that's a good thing. That's the property we want of a hash function. So we've got anything of any size can be fed into a hash function.
I remember watching this video.
Exact 64 hexadecimal character fingerprint of what that data is. It's deterministic. It's one directional. You can't go back the other way. It's really easy to make a hash. It's really hard to guess the secret of the hash. And what we can do with this is some really neat stuff about even like a Merkle tree is what it's called. So that would be something more like, let's see what we want to do here. Let's grab all of it and just copy and paste it a few times. Oh man, this is gonna make a mess. Here we go. Okay, so wow. So we've got, here, let me just zoom out a little bit. There we go. Okay, so we've got our 3 inputs. Okay, and we could join those together, and we can basically combine those, and we could combine all of those hashes, and then hash the combination. Oh, whoops, come here now. Throw another hash in there. Okay. Ooh, actually, I kind of want the color. The color's cool. Get out of here. Over here. Okay, so this color right here, that purple, represents the hash of all of these hashes. So if I change hello world to hello world 1, that purple is going to change. Any little change to any of these is going to cause my final hash to change. So I can bring in all sorts of data in all sorts of different ways, even have like a tree of hashes, or a Merkle tree, I think is what it's called, of all these hashes, or have a bunch of blocks in a row. And this final hash is going to be based on all of these things. If any little thing changes anywhere along the way, this final hash is going to change. And we'll need this property later on. But I think the key takeaway is to say, okay, well, I know that a hash function is basically like a fingerprint, and if I type in something, it's going to deterministically give me that thing that I expect it to give me. Okay, awesome. Thank you. That is a hash function. Welcome to ETH build. Let's make some cool stuff and learn a lot along. Okay, so the first video we used a hash. A hash will be important moving forward, but I think the next most important piece. Okay, so let's bring it in. So let's just look at these inputs now. So basically, the most important piece of the key pair is the private key. Let's just go ahead and generate one of those looks like. There we go. Okay, so and I can just click, and generate it's basically a random. I'm guessing it's the same size, 64. That's the same size as our hash that we were just doing. Okay, so it's a random 64 character.
Problem for the website is that there's also the added complexity of making it work, making it display on the site. That's why I'm still thinking about whether or not I'm gonna continue with that website after the demo day. But I think what I'm gonna do is first the data analysis stuff. Yeah.
Hexadecimal string. So you start with that as your private key, and then using this side quest, check it out on Wikipedia, elliptic curve cryptography, we will derive a public key. So now we've got a private key and a public key. We just generated a private key out of the blue, wherever we want. We just put it in another random one. Okay, then this is an address. This is where people actually send money, right? So this is sort of like when someone says send my Ethereum address. That's what this guy is right here. And a lot of times it's actually even display it as an address with a little locky. There we go. Isn't that nice? So if I wanted to create an account in Wells Fargo, I would have to drive down to the bank and give it a bunch of information, and it would be a headache, and it would take a while to generate an account within a cryptographic system like this, where I can send and receive money. I just generate this private key. This private key is everything. The 64 character hexadecimal basically derives everything else, and so there's a really neat property about this key pair that we should explore, and that is signing and recovering messages. So let's see how that works. So basically, what you do is you take your private key and you use it to sign some kind of message. Okay, so let's get a text box here and type what would your message be? Something there is if you with money. Okay, cool. So then we plug that in as our message. Okay, and I think it's just set auto sign. I have a button here that sign, but it's going to have auto sign, so Twitter. And this will give us back a signature. Okay, so if this changes, see how it comes with the hash, right? Our signature is basically taking the message and our private key, and we're signing something. And so what we get out of that is a signature. Now, I can send this out to the world. I can send this publicly to everyone, this string here, along with the message. And what the world can do, what anybody can do with that is verify that I'm the guy who signed it. I'm going to show you how we do that. What we do is we use a recovery method. So we plug our, actually let's do this completely separate because it'll look cool. So we need a couple text boxes. Hey. Okay, we've got a couple text boxes, one for the signature and one for the message. Oops, I got those backwards, crossed screens. Okay, here we go. So we need to plug in first our message, that there's the key with money. Okay, and then we'll plug in our signature. Okay, there we go. Now what comes out of that is the address that was used to sign it. What was going on here? There we go. We have a space there. Okay, we got 3289. And just we'll use Alex Van blockies to visually see that account signed that message. And there's no way, if anybody's like, well, maybe it's a badger. Yeah, everything changes. Even with that same signature, the message, it does spell an address, but it doesn't spell the correct address. So this message here can't be tampered with. We can throw a timestamp in there if we want to, right? We can say, on this day, I predict that something will happen, and sign it, and put out the signature, put out the message, and anyone from the first time with math can just prove that you did sign that message at that time. So this is the key property of a key pair here. A key pair generated from nothing more than this 64 character hexadecimal random string can be used to sign a message, and then that message can be recovered. So message plus key pair equals signature, signature plus message equals public address, right? Or public key. So private key, message, signature, message, public key. Does that make sense? Okay, that's basically the key piece here, is that we can sign data with our private key, and people can prove that it was us that signed it. And that'll be an important piece of the next step. Awesome. Transactions in blocks, package in blocks, mined into a chain, right? So we want to talk about packaging now, or at least what incentivizes the miner other than the block reward to pull our transaction out of the pool and put it into a block and mine it out of the chain compared to other people in the pool, right? Thousands of people in the pool that sort of bidding, right? And so that bid is with this fee, right? So I can have some fee in my transaction that says like, okay, I'm Alice and I'm sending 5 to Bob, right? And our announcement 1, the replay protection if you watch the distributed later episode, but also we will, let whoever mines this take a fee of a nickel to even a nickel for yourself, Sonny. So basically Alice is sending 5 to Bob, but also paying the miner a nickel to put it into the chain. Cool. Okay, so what does a transaction look like? on Ethereum. So we won't have Bob and Alice anymore, right? We'll have addresses, and the value is actually, this would be in Gwei, not in ETH, and we'll kind of cover that in a second also. And we're going to kind of have this fee that will be not in ETH either, but in Gwei, right? So this will be Gwei, and this is 5 Gwei. We'll talk about that in a second. But let's jump in and look at this transaction and kind of start messing around with it. So we've got I got an account, and I'm going to just drop in the mnemonic there, and I hook up to the Ethereum mainnet there, and I'm also running a this little module to go get the price data from CoinMarketCap. So now I can, when I see that I have 0.1 ETH, I want to multiply that by this number, so then I can just say I have a dollar now, right? And that's what we get out here. We're going to hook that up. Okay, so this account, this mnemonic, that's over seed phrase that I dropped in here, has $23 on ETH. So what I'm going to do is we want to send some of that, right? We want to create a transaction and incentivize the miner to pick it up and put it on chain. So we'll plug our private key in here. Let's missing the address here. Let's wire up the address while we're here. Cool. Okay, so now we need to send some to someone. So I'm actually going to duplicate this part. Actually, you know what? I'm going to want to know balance and everything. Let's grab all that. This is going to get kind of messy. Let me move it around here. Okay, so now I'm going to have two guys. I'm going to drop in this guy's mnemonic here. It'll be a different guy, and he probably I bet he doesn't have $23. Something's not wired up right here. What's going on? Oh, I forgot to do this. I need to bring the balance function. Okay, now there's that guy. That's going to go $0. So I've got two characters here. We can call these Alice and Bob if you want, and they are. Alice is going to send with her private key some value to Bob, so I want to put Bob's address in there. All right, and let's see how this is starting to take shape here. All right. So we see that there's no firm address here because it's going to be, remember, we're signing and recovering with our key pair, so it will package it up and it will sign it, and then that'll go across the network, no one can tamper with it, and on the other side, someone can recover it and find that it was indeed us that signed it, and so that would, the firm address is sort of derived. So also, let's just ignore gas right now, but we've got our 2, we've got our from that's being derived. Right now our value is null because I haven't put anything in, but let's just put in Hondo. Data is empty, let's ignore that right now. Gas, ignore that right now, that's actually a limit, but gas price is what's important here, and that's what we're talking about. And what it is, it's at 4 billion, right? 4.1 billion, which is actually a giveaway. So we're at 4.1 Gwei, and that's just like, it's just doing that by default. What we want to do is sort of be more strategic about it and see what's going on chain right now. And we can see that this last block, our block 242, had 78 transactions, and the gas price ranged from 35 to, I think it was 5. So basically, we would need to be above 5 to get money to that block. So let's go back to the gas price here and put in 5.001, right? Just a little bit more. Okay, so what I'm noticing here is we need to do conversion to Gwei. Ooh, what did I do? 2 Gwei. And what that does is just turns that 5.1, and now if we see that, it turns it into that, 5 billion. And I put that into my gas price. All right, so now I guess we should talk about Gwei too. So I'm sending 100 wet, right? And so it's actually, since you don't do decimals in, so it's an unsigned integer, right? So there's no decimals. So what we do is we sort of have this this idea that there are basically 18 decimals, and then that's where 1 starts. So you say, even though the value on chain would be this giant number, we call that 1 ETH, right? So 1 Gwei, right? Does that make sense how that's kind of divided up? So what we need to do is also, so we look at our Gwei, it's that number, but what we want to do is go to Gwei to make the transaction. What am I doing? Here we go. 2 Gwei, and so if I plug 100 in here, now I'm sending 100 ETH, which actually comes out to that, right? And so I definitely don't have 100 ETH to send, so we'll have to look at this guy's balance. What is this guy's balance in ETH? Is 0.18, right? So how many 0.18 we're going to send? 0.5 or 0.05, right? Yeah. And that in Gwei comes out to this, and you can see this. So we can see that these numbers are, since we got decimals, we can multiply them. Okay, so we got a transaction ready to go. We've got Alice's private key plugged in here. She's going to send to Bob. She has 0.18, and we're going to send 0.05, and we're ignoring everything else and saying that we're going to put in a gas price of 5, and so we need to sign that, right? So when Alice chooses to sign that, it's going to shoot out here, and so we'll grab. Well, let's just sign it. Let's just sign it together, right? Cool. There it is. There's a signed transaction. So that can go across the network. No one can mess with it. On the other side, someone can derive that it was Alice that signed it, and it will contain all this information of who we want to send to and our gas to go to the miner. So what do we do with that? Well, we can go over to our blockchain block over here and grab the send function and plug that in there and plug that in there. Now we've got, whoops, hey, what did I do? What have I done? This goes in here. Okay, so now we want to send that on chain, and when I click that, there we go. So it gives us a hash. So that is the hash of the transaction. So basically, I sent it to someone on this distributed network, right? And I said, hey, here's my transaction, and they gave me back the hash, or probably in fact it's calculated from the transaction. I have the transaction hash. It goes out on the network, and then what's going to happen now is basically there's a pool of all these transactions of these people all bidding to get their transaction to go through. So we can go look at the block. Looks like 50. What was the smallest? 5? Oh, we probably got in. Yeah. Okay, so now we want to query the blockchain. I bet it's already happened for our transaction, and we'll throw in this hash. Cool. Yeah, let's put that on timer. Yeah. Okay. Now this should show us our transaction. And sure enough, yep, block number. We'll just call it 258. Throw that in here. Let's go. Have a look. Let's go have a look. And let's sort. I'm gonna sort by gas price, but reverse. Whoa, what have I done? Sort by. So I'm going to look at the lowest to see how close I was to the bottom of the block there. Okay, so we can see 5. Oh, look at that sneaking in there, 5.001. Yeah, so there's old Alice, there's old Bob. No data, but we can see that we're in there for 5 Gwei. So there we go. We just sent a transaction. So the next thing to look at is sort of that data field. What's going on? So we are saying value. We're able to bid on it. We're able to kind of get our transaction recognized on chain. You can see we just sent Alice just sent Bob that $6. Let's look at one last thing here, and that is this data field. So we can send stuff along with our message, right? And it's actually going to be in hex. Boom, 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 boom. So what should Alice send? So she's going to send another $6 over to Bob. And if we look at that, let's just turn that into that. And can you go, hey Bob? No, just hey Bob. We're just going to go hey Bob. So here's hey Bob. We're about to put this on the Ethereum now. What are we doing? Okay. There we go. There's hey Bob in hash. We're going to sign that transaction. It'll give us send it out to miner, go to the network. You'll give us a hash back, and now we're watching for that to get money to a block, and there it did. Radical. So now we're gonna check that block. We should hopefully. Oh man, I hit enter and reload. That's what's going on. Okay. So here is our block. Where's the dude rolling the 5.001? There it is. Okay, so there it might be in, but now check it out. We sent a little data along, and let's even go a step further. Let's look at the price that we paid for it for the last piece of this. So I'm gonna copy Bob's address, and I'm gonna go to. Okay, here are the 2 transactions on Etherscan. So from Alice to Bob, 0.05 Ether, which is $6 sent for that 1 penny transaction fee, which was 5.001 Gwei. Okay, so we basically crafted the transaction, we signed it out to the network. Within that transaction, there was this gas price that we were willing to pay, and that incentivized the miner to mine it into the chain of blocks. Then we did another transaction where we sent along some input data along with this. So we sent the $6.37 from Alice to Bob, but also we said, hey Bob. So we said hi Bob. We brought some data along with the transaction, and there's all sorts of really cool stuff we can do now that we kind of have this call data coming along with it, and we'll get to smart contracts and a lot of fun stuff later. Let's look at one last transaction. So I just put this transaction from Alice to Bob into the transaction pool, but with 0.00, like 1.001. GUI for my gas price. And so it's sitting there unmined, right? Like it's sitting in the transaction pool. We can see that it's pending. If we go look at the transaction pool, so I have there we go. So I have a node running, full node running. I can talk to that locally, and you can just use the TX pool thing, TX pool in the Web3 section. But basically, we can see my transaction is sitting here. We can see my gas. But we can, if we look at this, we can see that the pool is between 1 and 300. But if we look at the latest blocks that are being mined, you know, the smallest amount is like 5, right? So we're just not incentivizing the miners enough. So we need to resubmit this transaction. Let's bump it up to 10. Let's go big. So that's way more than it needs to be probably. But we'll re-sign the same transaction with the same nonce, but with a new higher gas price, and the network will say, oh, this guy's like same guy, same transaction is willing to pay more. Let's see if we see it update over here on the. Basically, I'm signing this, putting it on the network, and saying willing to, you know, oh, that transaction, well, I'll pay some more for it, right? And it'll speed it up, hopefully, and hopefully we'll see it get mined into the next block here. We'll see. So we're at 365. So hopefully 10 was enough, right? Let's see if it got mined yet. Nope, not yet. So we're still waiting for it to get mined. Come on, blockchain. Oh, there it is. Okay, so it got mined into block 366. Cool. And there goes 367 already. But that was it. We set a transaction. We paid some gas to incentivize the miner to put it into the chain. Fun time had by all. Happy Go Time Friday. Thanks for checking out ETH Build. This was transactions. We'll get into some really fun smart contract stuff and some other side quests soon.
For Bitcoin, a transaction is simply a financial transfer, but for Ethereum, it's so much more, and it has to do with smart contracts. Hey, I'm Julian, and on ETH Blogs, I explain blockchain technology. On Ethereum, the most simple type of transaction is a financial transfer. Bob can send to at least a certain amount of Ether, the native cryptocurrency of Ethereum. When this happens, Bob has to send to Ethereum a data package called a transaction. This transaction contains the following fields. From, that's the address of Bob, and address is an identifier that identifies the account on the Ethereum blockchain. 2, that's the recipient of the transaction, so in our case, that's the address of Alice. Value, that's the amount of Ether that is transferred. To specify this field, we use a unit called weight. That's a small fraction of an Ether. 1 Ether equals 10 power 18 weight. So if you send 1 Ether, it's going to be 1 with 18 0 after. Then we have the data field, so for simple Ether transfer, this is going to be empty. Then we have the nonce, so this is an integer that is incremented for each transaction. This is used to order transaction on blockchain. All the nonce need to follow each other on blockchain. For example, if the last transaction that was sent to the Ethereum blockchain had a nonce of 4, for the next transaction, it needs to have a nonce of 5. If you try to send a new transaction with a nonce of 3 or 6, it's going to be rejected by the network. Then we have gas price to specify transaction fees. When you send a transaction to the Ethereum network, a miner will have to solve the proof of work algorithm in order to include your transaction in the blockchain. And to reward the miner for his work, you need to pay him with a transaction fee. The gas field, also called the gas limit, represents the computational difficulty of a transaction. So for a simple Ether transfer, this is 21,000, but for more advanced transaction, it's higher. So it might seem redundant for a simple Ether transaction because this is deterministic. We know in advance how much gas it's going to take. But for more advanced transaction, your transaction can take several execution paths, and so in this case, this gas limit field makes more sense. Then we have gas price to specify how much Ether we are willing to pay for each unit of gas. So we don't pay miners with gas, but we pay them with Ether. For example, if your gas price is 1 Ether, that means if your gas limit is 21,000, you are willing to pay the miner 21,000 Ether. Of course, that's way too much. So we specify gas price with a unit called GUI. 1 GUI equals 10 power minus 9 Ether. So if you specify a gas price of 100 GUI and your gas limit is 21,000, that means you are willing to pay the miner 21,000 times 100 GUI. And finally, the sender of the transaction has to sign the transaction, so that's the address of the from field. And this signature is used by the Ethereum network to verify the authenticity of the transaction. If anybody tries to send the Ether of another address, the signature is going to be wrong and the transaction will be rejected by the Ethereum network. Also, if you send your transaction to the Ethereum network and someone tries to change one of the parameters like the recipient, it will not match up with the signature and it will also be rejected by the network. In this signature, we also specify an identifier for each network, which prevents what we call replay attacks. So for example, if in the future the Ethereum network has a fork, you cannot take a transaction of one branch of the network and send it to another branch. When someone sends you some money, you can use this website to make sure that the transaction was actually sent. So here we have a transaction detail. So we're going to go over the main field. So here this is the transaction hash. That's basically an ID for the transaction. Each transaction has a unique transaction hash, then status. So it's possible for a transaction to succeed or fail. So here it succeeded. Then we have the block number in which the transaction was mined. Here we have the number of block confirmation. So that's the number of new blocks that were mined after the block in which your transaction was included. The more the block confirmation, the more secure your transaction. Because if a hacker was trying to fork the network and basically rewrite the history of the blockchain, it will take much more work if it has a lot of block confirmation, and very quickly it becomes impossible. Then we have the timestamp. So that's the time of the block in which your transaction was mined. Then you have a couple of fields from transaction like from to address, the value of Ether that was sent, the transaction fees. That's a combination of the gas limit and gas price parameter. Here the gas price in terms of way. Below we have the Ether price at the time of the transaction. So one important detail I forgot to mention is that here the account that pays the transaction fee is the sender of the transaction. So that is the from address. So in this case, that means that after this transaction, not only this amount was deducted from the from address, but also the transaction fee. And after you can see more detail here, yes, so gas limit parameter, how much gas was used in the transaction. So we used all the gas limit, and what was the nonce, so that was the 32nd transaction for this address. Okay, so that was a simple transaction, but what makes Ethereum really powerful is that we can make much more advanced transactions with a smart contract. Smart contracts are small programs that run on the Ethereum blockchain. With smart contracts, you can build things like decentralized exchanges, tokens, etc. When you hear about projects like Compound, Uniswap, under the hood they are implemented as smart contracts. To interact with smart contracts, we also use transactions. The transactions have the same fields, except that for the data field, it's not empty. For the from field, this is the sending address. The to field, this is the address of the smart contract. The value field, this is the amount of Ether you want to send to the smart contract. It can be 0 if you don't want to send anything. For the data field, that's where it gets interesting. The code of smart contract is organized in units called functions. Functions can be used to read or modify value in the smart contract. When you interact with the smart contract, you will execute one of these functions. The data field allows you to specify which function you want to call and which arguments you want to pass to the function. For example, if you call the transfer function of an ERC20 token, you need to specify the recipient address and the number of tokens that you want to send. To make it simple, I type the data field in plain text, but it's actually sent in hexadecimal form. And then you have the same fields as for simple transaction. So now things start to get exciting. With these advanced transactions, we can do more than just simple financial transfers. Can we push things even further by combining several advanced transactions together? What makes Ethereum really awesome is that one smart contract can interact with several other smart contracts. When you send a transaction to a smart contract, this smart contract can itself call other smart contracts with internal transactions, also called messages. For example, that's how we can have exchanges like Uniswap manipulate other smart contracts like ERC20 tokens. These internal transactions are similar to the ones I showed you before, except there is no signature. The behavior of a smart contract is entirely determined by their code. There is no need for signature. I show you how one outer transaction can result in several internal transactions, but how can we combine several outer transactions? For example, Bob sends some Ether to Alice, then Bob sends a transaction to a smart contract, then Alice sends a transaction to another smart contract, etc. On Ethereum, transactions are grouped in units called block. After each transaction, the state of Ethereum is changed. For example, after transaction 1, Bob has less Ether and Alice has more. After transaction 2, if Bob did a token transfer, he has less token and someone else has more, etc. Each transaction picks up the state after the previous transaction. So transaction ordering matters. As we always look at the final library to easily send Ethereum transaction. You might also want to dive deeper into the concept of gas, which is used for paying transaction fees. I'll see you there.
What I wanna know is how they were able to tell where the miners are from. Yeah, this thing here. I think is this. Or this one. I guess they did it manually, this one. Oh, it doesn't show the location. I thought it showed which country. They were from. Top 10 countries. Like, how do they know where they're from? Doesn't make any sense. I guess they do it manually. They just got the addresses and then link to the business. Yeah, I think I'm gonna stop here. I'm gonna watch the other videos off stream. And I think I might come back tomorrow and try to do... I'm not sure if I'm gonna focus more on the data analysis stuff or trying to attempt to create a graph for the miners page before the demo day. Because I don't think I'm gonna have enough time to create the graph and the page before. But it might be worth trying. But if it wasn't for demo day, I think I would definitely focus more on the data analysis part instead of the visualization stuff, because I'm not sure if I'm gonna continue with the website. Well, the data comes first and then the website comes later. So I might come back tomorrow, or maybe not. But if not, then probably after demo day to continue doing this stuff. So see you then.